An interesting thing to be able to do is to write out what is described as the electron configuration. An electron configuration is simply a description of how many electrons an atom has in each of its subshell. And the electron configuration is written by listing each of the subshells in order of increasing energy. So we're going to start at all of those subshells that are in the first shell and then work our way up to all of the subshells that are in the last shell. And how we do this is by using a superscript that following the symbol for the subshell to indicate how many electrons are in that subshell. Now, this is a good example here. This is the description of an atom. It contains a total of 2 plus 2 plus 4, that equals 8 electrons. 2 of those electrons are in the 1s subshell, 2 of them are in the 2s subshell, and the last 4 are in the 2p subshell. So that's what's going on. That's a classic electron configuration. So when we build up the electron configuration of an atom that has more than one electron, we're going to use this thing called the Aufbau principle. And Aufbau is just a German word for building up. And what we do is we start by putting electrons in the lowest energy subshell first, and then we work our way up towards the highest energy subshell. So the energy of the subshells follows a fairly complicated order. For the first couple of levels, it's fairly obvious the order that it follows, but there is a little bit of a difficulty. These are the shells: n equals 1, n equals 2, n equals 3, n equals 4, and the difficulty that we have is that as we go to higher and higher shells, they kind of get bunched up, and then all of these subshells kind of start overlapping. So you can see that some of the subshells that are in the fourth shell here start overlapping with some of those that are in the third, and then when we get higher up, some of those that are in the fifth shell start overlapping with those that are in the fourth, and it just gets worse and worse the higher that we go up. However, there is hope. Rather than having to memorize this complicated sequence, what we can do is we can use this thing called the Aufbau diagram, and should always have a copy of the Aufbau diagram handy or be able to recreate it. And because it makes the order of filling of the subshells really easy to remember. So what we do is we write a column where we list a 1s down to 7s. And then starting at row 2, we write 2p down to 7p. Then starting at row 3, we write 3d down to, you can put 7d in there, it doesn't make any difference. We just won't be using it. And then at row 4, you start 4f and you write down to 7f. Now the order of filling is determined by these arrows here. So we draw arrows in on the diagonal like so. And what we do is we keep in mind that in an S subshell, we put 2 electrons. In a P subshell, we put 6 electrons. In a D, we put 10 electrons. And in an F, we put 14 electrons. And then we just work along the arrows. When we get to the end of an arrow, we go back to the next one. And this gives us the correct order, including all of those weird exceptions that we saw in the previous diagram. So as long as you've got this guy handy and you know the maximum number of electrons that can go into a particular subshell, you can write the electron configuration for any atom. So say I want to write the electron configuration for sodium. Sodium has atomic number 11, so I know it needs 11 electrons. So I'm going to do 1s2. Now that guy's filled. So now I go to this arrow, 2s2. So that one's filled. So I go to the end of my next arrow, 2p, and now that can have 6, so that's filled. And then I'm still not at 11, I'm only at 10. So then I go 3s, because I'm in here, and I need to put 1 in there. And there you go, I've got the electron configuration for a sodium atom. And it's got 2 plus 2 plus 6 plus 1, and that adds up to 11 electrons. So super easy if you've got the Aufbau diagram and know how to use it. So we're going to do the electron configurations of the first 3 periods, and I've put the Aufbau diagram here so you can see how I'm doing it. So period 1 is nice and easy. It only has 2 elements in it. Hydrogen, which has atomic number 1, which means it has 1 electron. So it's going to go 1s1. Helium has atomic number 2, so it's got 2 electrons. So we go 1s2. So at that point, the 1s is finished, and I got to come over and start filling up from there. So period 2 has these elements in it: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Neon goes all the way up to element number 10. Lithium is element number 3. So lithium has 3 electrons, 1s2, now that's filled, 2s1. Beryllium has 4, so it's 1s2, 2s2, and now the 2s is filled, so I'm over here. Boron has 5, 1s2, 2s2, 2p1. Now it gets a little boring because as I'm moving through carbon, nitrogen, oxygen, fluorine, and neon, I'm just filling up this 2p subshell. So it goes 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, all the way up to neon when the 2p gets filled, and now I'm on to the 3s. So in period 3, I'm going to pick up filling up at the 3s. That's where I was up to, okay? So these are the elements: sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Sodium has 11 electrons, argon has 18. So it goes 1s2, 2s2, 2p6, 3s1. And then we've got magnesium with 12 electrons, 1s2, 2s2, 2p6, 3s2. And now the 3s is filled. Then we're on to aluminum with 13 electrons, 1s2, 2s2, 2p6, 3s2, 3p1. See, we're in here now. And then as we move across the rest of them up to argon, we're just filling up this 3p subshell. Okay. So what you see is that these guys have a lot of their electron configuration in common. There are these electrons that are not in the outermost layer. They're what we refer to sometimes as the core electrons. They're in they're in the inner layers of electrons. And they're not really going to do, these. It's kind of frustrating writing these out again and again and again. It would be nice to have a shorthand for that. That's one thing. But the other thing to recognize is it is these electrons that are in the outermost layer that are going to be used to interact with other atoms. These guys that are in the third layer here are the interesting electrons from a chemist's perspective. So the outer electrons in the high shell are those responsible for an atom's chemical properties. They're the ones that is going to be that they're going to use to interact with other atoms. The core electrons in the completely filled inner shells, they're not so interesting. They don't contribute as much to an atom's chemical property. So what we can do is we can abbreviate the electron configuration to focus on the chemically interesting electrons that are found in the outermost shell. So I'll show you how we do that in a moment. So let's have a look at these 2 electron configurations. This is for potassium, element number 19, and this is for calcium, element number 20. So in each case you see that these are the electrons that are in the outer shell, which is the 4th shell. And then the electrons that are in shells 1 through 3, those are the core electrons. And you'll find that there is 18 of those. And they are in the configuration that is found for argon. So how we can kind of abbreviate this so that we can just focus on those chemically interesting outer electrons is we can replace all of these core electrons for with the symbol for argon. So what we can do is we can write what we call the condensed electron configuration, where we substitute the symbol of argon and we put it in square brackets for the core electrons. You see what we're doing here? So here's the full electron configuration. We want to focus our attention on these outer electrons. So we're going to replace the electron configuration for the core 18 electrons with the symbol of argon in square brackets. And then now we know we're just kind of focusing on these chemically interesting outer electrons. So we can do this for any element. We can write the condensed electron configuration of any element. And what we do is we write the symbol of the noble gas that comes before, instead of writing out the electron configuration for the core electrons, and then we just write in the added electrons that are needed to finish off the electron configuration. So sodium has 11 electrons, and the preceding noble gas, the sodium, is neon, which has 10 electrons. So we know that we just have to write the electron configuration for the last one electron. So how we abbreviate that, we're just going to replace these with the symbol for neon. Now, magnesium has 12 electrons. The noble gas that comes before magnesium is also neon, so we can use that to replace the 10 core electrons, and then we just write the electron configuration for the outer 2 electrons. So again, we're just going to replace this with the symbol of neon. And we can do this for any element. We're just going to replace the electron configuration for the core electrons with this symbol for the preceding noble gas written in square brackets. Okay, so that's how we write an electron configuration. So an electron configuration tells us how many electrons are in each of an atom's subshell. There's two ways of writing it. One is what we call the complete or full electron configuration, where we specify the number of electrons in every subshell explicitly. And then we have the abbreviated or condensed electron configuration, where we focus our attention just on those electrons that are in the outermost shell. When we write the condensed electron configuration, what we do is we substitute what are referred to as the core electrons electron configuration with the symbol of the element's preceding noble, or with the symbol of the noble gas that comes before the element written in square brackets. Okay.